Welcome to today's session. We are going to finally conclude our discussion on population growth and decay models. Whoopsie, what's that line doing there? Don't be there, line. So let's just have a quick review because I find a lot of value in having a big picture of what is happening here. So I'm not going to do the whole thing. I specifically want to remember our basic exponential growth model, which said that the rate of change or the growth rate was proportional or is proportional to the population size at that time, giving us this equation. And we solved that differential equation and we saw what the function looks like and all that. Then we did radioactive decay, and it turned out to be the same differential equation with just a negative constant here, calling it the decay constant, but nothing really changed too much. It was just the other side of the exponential graph that came out of us as a solution of this. Then we said in number 3, we want to have exponential growth of some kind, or let's say proportional growth, but there should be some capacity aspect built in, where if we now look at the situation practically and keep track of how things grow out there, soon or after a while, the space becomes a limiting factor. So instead of 1, we can try to have the growth rate be proportional to the difference from or between some capacity, a fixed constant capacity due to space, and our population size at that time. Then the closer the population is to this maximum capacity, the slower it's going to grow, which is what actually happens. But not initially. Initially, the population grows without any consideration of that capacity. It's only when it gets closer to that capacity uh, it starts to affect the growth rate. So we did some other things here. Number 4 was Newton's law of cooling. Number 5 was some mixture problems. Okay, great. I'm not going to worry about those. I'm going to worry about these 2. In our logistic model, we are now going to combine these 2 and say that, well, okay, I want the best of both worlds. I want this first one initially, because that seems to be what's happening. If I actually put fruit flies in a jar, give them some food, it grows almost perfectly according to number 1 up to a point where the space limitation becomes important. And then it switches to the second one. So I want to have a mix of both. If the growth rate is proportional to the population size and it's proportional to the difference to the capacity, well then then the growth rate is going to be proportional to the product of the 2. Because if the population increases, it's going to push up this right side and the growth rate. But if the difference, let's say the gap to the capacity, if it gets closer to the capacity, then this gap in the bracket gets smaller and it pulls the growth rate back down. So this is going to be our logistic model. Now, we could totally solve this in general and have a formula, but I find that I get caught up in the general technicalities almost too much, and I can get more benefit right now as an introduction from looking at specific examples. So let's do that. And I just took an excerpt from a random book, and our first example, let's have a look at it. So let's say here the logistic equation may be used like we did for number 1 to model how a rumor spreads through a group of people. So we're going to let P then represent the fraction of people that have heard the rumor on day T, and we have this familiar logistic equation where I have some growth constant. It's now proportional to the quote-unquote population size and the gap to 100% capacity, of course. So 1 is my capacity. And that describes how P changes. So not a Y, I'm going to use a P. Suppose initially 1/10 of the people have heard the rumor. That is P of 0 is 0.1. So I am going to, it doesn't really matter. Whether you use a big P, I think we used a big P last time, or a little p, that doesn't really matter. So initially I have 0.1. So let's just write that down. So in our example, now we're not using a Y, we're using a P. It doesn't matter at all. I have a specific growth constant, and I have my capacity of 100%, so 1 there, and initially I have 10% of the population knowing the rumor. So then we need to, I'm not going to do these in order. I want to find the formula first. I want to solve this differential equation first and see what that looks like. So now, of course, this is a combination of type 1 and 3, a more complicated differential equation, absolutely, but it is still a separable differential equation where I'll take the p and the 1 minus p to the left, and I'll keep the proportionality constant on the right as always, and now I have to integrate that. Now the right hand side, super easy. The left hand side, not so much. Now I don't want to go into too much detail here. We can expand this and break it up over this not common denominator as much, but if I have a product in the denominator, I can split it up as something, and we'll get into the something in a second, over the first factor plus something else over the second factor. This can be done in more detail. It's called partial fractions, but our initial expression is simple enough that we don't have to worry too much about the topic in general. Now I can just sort of guess and check my way through this by thinking, okay, well, the numbers are quite simple. I can put a 1 in either numerator, and does that work? Well, if I now put these fractions together over a common denominator, I'll get the first one times the second one, so I'll get over p 1 minus p. For the first one, I'll get 1 times 1 minus p, plus for the other one, I get 1 times p, the other denominator. So the p's will cancel, and I get my 1, which I want. Okay, so reverse guess and checking is going to be sufficient for this level of fraction. But in general, there is a solution strategy here called partial fractions for how I can expand something that looks like this. We don't need to go into too much detail because We just need it for these specific, fairly simple looking ones. And we can easily check if our guess is correct. Okay, why did I do that? Because now I can handle these guys more easily, right? The antiderivative of 1 over p is natural log of p. Antiderivative of 1 over 1 minus p, yeah, log of 1 minus p, but I'm going to have a negative there. And then the right-hand side is fairly easy. Well, very easy. I have my integration constant there as well. Okay. So that is what we have so far. Now we just have to solve for p because I want to see the function. I want to see what does this look like, then what happens long term, and so on. So because our initial differential equation was a little tedious, the solution process is as well. But it is a necessary process that we should see a couple of times at least. Now I'm going to put these two left terms together with a log property. Log of the difference of logs is the log of the quotient. A property we may not be using a lot, but it is there when we need it. And so p over 1 minus p is e to the point 2t plus c. I'm going to do the same thing as we've done before by having a more convenient version of the integration constant. So now, unfortunately, it's not quite done, but I do have my general solution here, and an option certainly is at this stage to use my initial condition. Oops, not y, it's a p. To use my initial condition to say that, or to find the integration constant. So p is 0.1, and so 1 minus p is 0.9, and that is going to give me e to the 0.2 times 0 for t, and again, like always, that is going to be 1 when time is 0. So m is, I can simplify it to 1 over 9, unfortunately a repeating decimal, so I will leave it in this fraction form. Okay, so now let's go back here. So I can now put in my integration constant as 1 over 9. Unfortunate little fraction there. Yeah, just have to deal with it. And now I'm going to multiply both sides by 1 minus p to get, I'll leave this guy in front here, e to the point 2t, 1 minus p, then becomes the exponential portion multiplied in. It is quite tedious to solve this, but worth seeing a couple of times before doing it in general and trying to plug things into a formula. Formulas don't promote understanding, they promote sort of efficiency, get to an answer, and they encourage to not understand, and that can be dangerous in the beginning. So let's see, where are we now? I want to solve for p, so I'm going to take this guy to the other side. So p, I don't want to skip too many steps. For anyone who's watching, this would be the first time you see the logistic model, so you might not be super comfortable with all these differential equations and simplifications and all those things. That's the level we're at. We're not at a pro level here. We're learning. So then I can factor out a p on the left to get 1 plus 1 over 9 e to the point 2t. It's going to look fine in the end. It's just a little tedious to get there. 1 over 9 e to the point 2t. And so p I can finally solve, and I'm going to make this look a little better as well. The right hand side over this bracket. Now a little tedious algebra. I'm going to divide by this numerator throughout, and then it's going to be 1 over 9 e to the negative 0.2t plus 1. And that's going to be my best looking answer. Best looking answer. Now this is a function like any other, but it's perhaps not as easy as it was before to just use the basic exponential function and transform it a few times to get that. If I put this into graphing calculator, whatever I have nearby, there are free options on the internet. I graph this, I get something that looks like this. So we now see, I just used an X there, I wasn't sure if it cared. That is our function, right? Point 2. Did I use a point 2? Did I use the 2? Oh, I used the 2. Okay, whoopsie. Let's fix that. Point 2. That's okay. Just scales my time frame a little bit. The essence is still there. It's just so slow. I'm actually going to put a 2 there just so we could see the shape a little bit better. Otherwise, things are so flattened out, we don't get the nice curvature as immediately apparent. It doesn't change, it just stretches the time frame. So what I see here is I have my initial population size of 0.1, and initially I have an exponential, basic exponential growth, but very quickly it's going to sort of turn and become that capacity shape that we saw. It's just a mixture of the two. So it starts basic exponential, then it realizes, oops, I have some space limitations for whatever reason it may be. And then it starts to turn into that capacity curve that we saw in the third kind of model. So I have this mix of the two that we are looking for. My capacity here, I see long term is my 1, which is 100%. So we can write that down, but you can see it here. The capacity is 1, and that made total sense because our capacity was up here, built in there, and that is the 1 for 100%. What other questions do they ask here? At what time, okay, we're going to get to that in a second. I'm going to do the D one first. How long does it take before 80% of the people have heard the rumor? Well, I have the function. It's not a challenge, is it? It was maybe looked like a challenge to get to this function. But now that I have the function, I can answer whatever question you want. So, for example, if I want to know how long it's going to take for 80% of the people to know the rumor, we can do that. If I want to know how many, let's do an easier one first. Let's say D1. How many know the rumor after, what shall we say here? What time frame? I don't know. After 2 days. Well, we have our function. We just plug in a 2. So I'm just going to copy it there so you can see it. Now maybe 2 isn't a great example, but that's okay. E to the negative 0.2 times 2 plus 1. And let's see in MathBot, what do you have for me today? So just watch your brackets and be careful in how you're calculating this. 1 divided by everything in brackets. 9 times e to the power of, I'll put that in brackets as well, negative 0.2 times 2, though I could shorten that. my head, and then of course the +1 there. MathBot says, yeah, not a lot. I didn't let a lot of days pass. 0.1422 if I round to 2 decimal places. So that means approximately 14.22% of the people know the rumor after 2 days. If I then ask, as in D, when do 20, not 20%, when would 80% of the people know the rumor? Well, I just solve for P, not solve for P, solve for T time, and I have P is 0.8. So now I plug in 0.8 for P, and I'm looking to solve for time, which is essentially the same as what we've done before. I just have to flip these things around a little bit. So 9e to the negative 0.2t all plus 1 equals 1 over 0.8. We could simplify that 1 over 0.8 first if we want to. I'll just show it in chat. I'm not saying it's hard, but no one is speaking in chat right now, so I'll just show you something. 1.25. So then 9e to the negative 0.2t. I don't want to skip too many steps. You never know who is watching. 0.25 by subtracting this 1 on either side. And so e to the negative 0.2t is 0.25 over 9. I'm just going to put it over here. Negative 0.2t is the natural log. Oops, that looks like a u. That's an ln. 0.25 over 9. So t is natural log 0.25 over 9 over negative 0.2. Let's see what we get here. 80% is pretty high. So how long does it take for a lot of people to know the rumor? So I have natural log 0.25 divided by 9 divided by negative 0.2. MathBot says 17.9176. So approximately 18 days. And then 80% of the people will know the rumor. All right. So it does take us a while to go through these, but it's a more complicated differential equation. Short videos is not really what math is going to be all about, but we can certainly do this in 2 parts. I want to say a little bit more right now. So what have we done? We have our function somewhere over here. There's a function describing how this changes, and we saw I don't have a lot of space here. I'll just squeeze it in here. As time changes, my population grows exponentially, and then it turns to the capacity of 100% of 1. So best of both worlds, which is exactly what I wanted to do. I could look at this a little bit differently by checking how much space I have. Oh, I have some space, okay. So let's look at this a little bit differently. Let's say, let's just write down my differential equation again. I had 0.2p, 1 minus p. Okay, so this is the growth rate of the population. Now forget that it's a percentage. Think of it as individuals. the growth rate of the number of individuals is proportional to the number of individuals, excuse me, and then this difference as well. If I divide both sides by p, then I get 0.2 times 1 minus p on the right, of course. Now, when I divide by the total number of people, so to speak, I get what's called the per capita growth rate. The growth rate per person, if you will. Growth rate per person. If I Yes. If we look at this versus my basic exponential growth model, there we said dy dt is proportional to just the population size, and the per capita growth rate is a constant. Here, we can see the logistic model as a generalization of the per capita growth rate. That per person, the growth rate isn't constant for very long. It's constant up to a point where there are too many individuals. Then it's going to slow down. But the basic model doesn't have that. It says it keeps going. It doesn't slow down regardless of how many people there are. If we expand or generalize a constant on the right, a constant function on the right, to a next step up, it would generalize to a linear function, a straight line, which is exactly what this one on the left is. This has a slope and a change, and there's a negative slope. So you see here, you can even write it as in the y equals mx plus b form, but it's not x or y. You see here we have a negative slope, meaning that the higher p goes, the lower this right-hand side becomes, the slower the per capita growth rate is. The per capita growth rate slows down, we'll say, or the growth rate slows down as p increases. So it's a little bit more general. So my linear right-hand side expression, if you will, generalizes the constant right-hand side from model 1. If we look at the per capita growth rate, in the very, very simplest case, it's always the same. It doesn't get affected by the actual population size. One step up, and it becomes a straight line, linear change. And then, of course, one can go further and make it quadratic and so on. But linear is a very big improvement, and the complexity in the differential equation is still manageable. That's one observation I want to make, and we will move ahead with that tomorrow, or the next day, ideally tomorrow, next time. But another note I want to make with my example, so we can get very far with just one example. You see, I don't like the look of that D. It bothers me. It's not pretty enough. We can get very far with just one example and see a lot of different aspects. One is just how the solution works, how the solution process works. How is this a generalization? How can I view it as a generalization? Well, two ways really. I can see it as a combination of these two. Well, if the growth rate is proportional to either one, it's proportional to the product. Then what do we get out of that? Ooh, it's actually very nice what we get out of that in the graph. Another version is to say, look at this per capita growth rate. Previously it was constant. What's the next generalization step up from constant? Linear function. Now we have our model. Instead of solving for p, finding my function that's a solution to this differential equation, I can look at or consider what happens to the left-hand side versus the right-hand side. Well, if I simplify the right-hand side to 0.2p minus 0.2p squared, I see that the right-hand side is quadratic. So the growth rate, not per capita, these are nuts, is a different note now. The growth rate is, I'll say, a quadratic function in p. And it's a simple quadratic function as well, because I can see the intercepts and everything. So if I graph that, it allows me to answer, now p is the horizontal axis, and the growth rate, dp dt is the vertical axis. It allows me to make some simple observations without having to solve the whole differential equation. This is a parabola. The legs are pointing down. I can see the quote-unquote p-intercepts here. One is 0, one is 1. So let me try and get a nice smooth-looking parabola over here. I have a little wobble there. This side is very tricky to draw without seeing my hand. There we go. That's good enough. 1 over there. So as p increases from 0 to 1, which is going to happen with time in the background passing, the growth rate is going to increase and the growth rate is going to decrease. You can see that in the graph, that the growth rate, which is still the slope of this line, this graph, slope increases up to a point, the inflection point. And then that's as fast as it grows. Fastest growth. And then it's going to slow down. Because I'm still looking at dp dt. So I'm not looking at the slope of this graph. I'm looking at the slope of the actual function. So the growth rate is going to increase and then it's going to slow down. That's just sort of verified by this way of looking at it. As the population growth, the value of dp dt goes up to a maximum point here. Now this maximum point corresponds to this inflection point. And then it's going to slow down again. I'm not saying those points are the same. This one has a p and a dp dt. This one has a time and a p-value. So it's not the same thing. But as time passes, we're traveling along this graph. As time passes, we're traveling along this graph, and they directly correspond to each other. So now the benefit of this guy is this is a simple parabola, and I know that this is going to happen exactly halfway between the two. So at 0.5, population 0.5. Remember, this is now proportions. It's not actual number of individuals. It means 50% of the population in our example, just to have numbers that are nice and simple to work with. That is when the population grows, the rumor grows the fastest. So the rumor spreads the fastest at population 0.5, which means 50% of the population knows the rumor. When 50% of the population know the rumor. When does that happen? So I'm trying to answer this question. At what time is P changing most rapidly? Part C. Well, I simply set P equal to 0.5, but I do have to go to my function, right? And my function was over here. But that's something we know how to do. That's not a challenge. Let me just scroll up a little bit and set that up. So 0.5 equals, where's my function? 1 over 9 e to the negative 0.2 t plus 1. And looking at the graph, let's actually just briefly look at the graph and see where do I think that happens. Ooh, it's so hard to judge where an inflection point is. It looks to sit, I wouldn't say on one, but it certainly could be. It seems for me, of course my scale isn't quite the same, right? Just a little after 1 on this version of the graph, just so I have a nice shape I can look at. So you can sort of judge it from the graph and get an idea, what should I be getting here? But it's of course not very accurate. So 9e to the 0.2 t plus 1 equals 1 over 1.5, so that's going to be a 2. So e to the negative 0.2 t is going to equal 1 over 9. So t is going to equal natural log 1 over 9 over negative 0.2. Let's see what that comes out to be. Natural log 1 over 9. I want to divide by negative 0.2 as well. I get 10.9861. So approximately 11 days. Zoom out on this. So there's a lot of benefit that I can get from looking at the relationship between different things. Yes, I could just solve my differential equation, get the function, get everything from that function, but that function could be a little bit less than ideal to work with. This isn't the easiest function to look at. If I can look at other things like the left-hand side versus the right-hand side in my differential equation, how does the growth rate change with the population size? And then that's just a simple quadratic relationship, which is easy to analyze. And I can say things like the growth is fastest when the population is halfway to the capacity. And then I can't forget my function. I do need the function to elaborate on that once I want to answer questions with time. But there are different ways to look at these things, and they both have their benefits. All right, we'll pause it here so we don't ramble on for too much, and I will see you next time.